This presentation is about structural integrity from the point of view of the history. It is written and prepared by myself, Professor Aleksandar Sedmak, and my colleague, Professor Milos Kovic. We are both from the University of Belgrade. Myself, I am from the Faculty of Mechanical Engineering, and Milos is from the Faculty of Philosophy. He is historian. This presentation is dedicated to the memory of Stojan Sedmak, who was the founder of fracture mechanics and structural integrity in ex-Yugoslavia and Southeast Europe region. Original version of the paper was published in a journal, Structural Integrity and Life, about 10 years ago. It is only natural to start this story with great pyramids, built more than 4 millennia before and served dominantly as the Egyptian pharaohs' tombs. Driving force for this spectacular building achievement was to show the power and immortality of pharaohs. With 146.6 meter height, the Great Pyramid, Cheops, the middle one, was the tallest man-made structure in the world until the 1880s, when 3 other man-made structures overpassed it: Washington Monument, Cologne Cathedral, and Eiffel Tower. So, Great Pyramid of Giza is still an integral object. Dimensions are slightly reduced after so long time due to some damage of outer surfaces, but obviously these pyramids are constructed for unlimited life. They are still the largest stone structures in the world. Both from historical and structural integrity points of view, it is still a mystery how these great pyramids were actually built. One interesting, relatively new theory was proposed by Davidovits in mid-80s last century, stating that the pyramids were cast in situ by using granular limestone aggregate and an alkali aluminosilicate based binder, something like a concrete structure. Following this proposal, Professor Barson from Drexel University, and originally from Egypt, and his research team applied scanning and transmission electron microscopy to investigate this possibility. Nevertheless, obtained results are still not definite, so we still wait for this or any other theory to be confirmed. In any case, as already mentioned, driving force to build such a monumental structure was to show the power. Now we shift about 3 millennia later to see the tale of Hagia Sophia in Istanbul. It was in the 6th century, only after a few weeks after destruction of the existing basilica, that Emperor Justinian I inaugurated the construction of a third and completely different basilica, larger and more majestic than its predecessors. So, even only by saying this, it is clear that once again the driving force for such a magnificent building was to show the power. And also, it was a kind of temptation and challenge to overpass similar constructions like Rome Pantheon or Solomon Temple. Nevertheless, Pantheons 43 meters in diameter were not reached, even not later on, despite few famous attempts like St. Peter's Dome in Vatican. Only in modern times, by using reinforced or pre-stressed concrete, there are some domes that surpassed Hagia Sophia, and one of them, which is still world record holder for pre-stress concrete structures, is hall number 1, Belgrade Fair in Serbia, built in 1957 with span of 109 meters, designed by academician Branko Žeželj. From the point of view of structural integrity, the main feature of Hagia Sophia is, of course, its dome, since it is still the largest, one of the largest in the world. And also, very important is to emphasize that the first one collapsed, so only the son of Justinian I, that is Justinian II, was to be a new builder of a dome which still stands. Not only construction itself, but also a region where it is positioned and which is very prone to earthquakes, contributed to the collapse of the first dome. Anyhow, that one was too flat and it could not sustain shear loads. So the new one was built by use of lighter materials, and even more important, it was built in almost hemispherical shape. It was also supported by 4 large columns. They form the Roman arch, including transferring elements which are extracts of spheres. So the weight load is distributed in the optimal way from the circular dome to the rectangular supporting structure. Later on, additional supporting elements were added on each 4 sides. So after it was built, reportedly Justinian II said, "Solomon, I have surpassed thee." So that is the crucial evidence what was behind the scene, what was inspiration and driving force for this magnificent. Now we go another millennia through time and focus on bridges. And bridges not only as a link between 2 banks, but also as link between times. And finally, a link between stone and steel. It is somewhat different now as for the driving force, as for the inspiration and motivation, definitely bridges are made to connect people, also to show ingenuity of their builders, and to some extent, finally, of course, the power of, let's call them, investors. So the first one that we mention here is famous stone bridge in Mostar. It actually replaced the original bridge made of wood, which was not good enough, and stone was to be used as a material to last, if not forever, then for a very long time. Construction began in mid-16th century and took about 9 years. Unfortunately, little is known about the construction itself. One of the legends that are still to be talked about is that its builder, Mimar Khairuddin, actually prepared his own funeral on the day that bridge was finally made, because he was not allowed to do anything like that again. And another interesting historical aspect of this story is what 17th century Ottoman explorer Evliya Çelebi wrote about the bridge. It is kind of poetic description, saying that bridge is like a rainbow arch soaring up to the skies, extending from one cliff to the other. Also very interesting from structural point of view and from integrity point of view is that this bridge was a kind of mystery until 50s of 20th century. Namely, calculations would bring to a conclusion that bridge structure cannot sustain its own weight, and thus one doctoral thesis and young ambitious scientist from University of Belgrade, Aleksandar were needed to actually prove that bridge was hollow and definitely much lighter than previously thought, and this is how it could sustain its own weight. Nevertheless, to get longer spans and larger bridges, it was inevitable to use metals instead of stone or any other material. So we have had to wait until late 18th century when iron production was finally commercialized and industrialized. So in Coalbrookdale, Thomas Fernald Pritchard finally suggested and made a bridge of cast iron. You can see it on the figure below to the left. Its structural integrity was jeopardized. Later on, you can see on the figure to the right some cracking, but that was taken care of. So in this case, we can see that motivation, which is basically to link people, also depends strongly on material to be used. and of course, at the same time, on human ingenuity to be capable to produce such a material, stronger and stiffer, and also to make a construction of such a material. About a century later, the power of iron was demonstrated in unprecedented way, since the Eiffel Tower, also called the Iron Woman, was constructed in 1889 as the entrance arch for the World Exhibition. It was named after its designer, Gustave Eiffel, famous engineer at the time. This 324-meter tall construction actually ended the race for the height in late 19th century, and about 50 years it was the tallest constructed object in the world. It was only in 1930 that it was overpassed by Empire State Building. Mostly, once again, the driving force or historical aspect of this construction was to show the power, in this case, the state power. It was to be shown to the whole world what France and Paris can make. Of course, at the same time, there was a strong challenge to use relatively new material and certainly new building techniques. And finally, but the most important, is that we notice the new structural shape which was designed to adopt wind forces as the main load. This iron construction weighs 7.3 thousand tons, and in total, including all other components, it is about 10,000 tons. It may shift away approximately 18 centimeters because of thermal expansion, and it also may sway in the wind up to 6 or 7 centimeters, and both without jeopardizing its structural integrity. Well, in any case, wind is here the main issue. As its constructor, Eiffel, said, he had to calculate what is the optimal shape to resist the wind. And that was not a simple mathematical calculation, because at that time we didn't have any computers. But as you can see, this construction still stands and its structural integrity is not questionable. But then again, there is another issue to be mentioned here, and that is regular maintenance. Because of environmental effects, practically all pieces or elements of this construction had to be changed or repaired or painted and protected from the corrosion, and so on. So all initial 18,000 pieces have been replaced at least 2 times until now. We can say that Eiffel Tower is an impressive proof that integrity of complex metallic structures can be ensured and saved. The race to the sky is best promoted and can be seen in this figure showing Burj Khalifa. It is more than 800 meters tall. It is both spectacular and beautiful, and it really introduced a number of innovation both in a structural way or from the point of view of materials that are used. The most important is its shape, nevertheless. So the floor plan of the tower consists of triaxial Y-shaped plan formed by three separate wings connected to a central core. That is the simplest and the best geometrical shape to resist wind load. And once again, wind is the most important problem that was to be solved. So also kind of spiral shape, as you can see in this figure, is an optimal design, an optimal geometry to resist wind load. Definitely, except for being a very efficient building, it was also intended for showing the power, in this case, power of United Emirates and Dubai. So the beauty and the beast at the same time. Nevertheless, we can't reach the sky unless we fly. So it is about aeronautical achievements that we shall discuss now. In the historical context, it is quite a complex issue, as we may say everything in aviation. Just to remind you that the first attempt to make a commercial passenger airplane with jet engines, which was back in 50s of 20th century, so the famous Comet series made in Great Britain, was stopped due to several failures. At that time, it was yet to be discovered that fatigue cracking was the major problem due to underestimated stress concentration factor or problem. Later on, the problem was solved and fatigue crack growth put to a control, just to mention famous Paris law. So for a couple of decades, it was Boeing that took over and was the front runner in ever increasing sizes of the airplanes. But then again, Europe's Airbus made the largest passenger airliner, A380, also representing one of the finest achievements in the history of structural integrity. Now, in this case, driving force was a bit different. For the first time, it was economy. But economy is a tricky issue, so after being a driving force, later on or nowadays, it actually is kind of a stopping force. Namely, as in the case of Concorde, it doesn't pay off anymore to make such a big airplane, so A380 is actually not produced anymore. Anyhow, Few technical details will be given in next 2 slides. Airplanes are of course not made of steel, they couldn't fly unless they are made of lighter materials like aluminum alloys or in recent decades ever increasing ratio of composite materials. In this case, we focus our attention to laser beam welded panels, which are marked in orange in this figure, and which were extensively tested in GKSS in Hamburg, Germany. You can see how the testing was prepared and also the final outcome of fatigue testing of a panel with 4 stringers and 3 clips after it failed. Data that was collected during these extensive testings actually showed that 4 stringers are beneficial and should be used to strengthen these panels, but at the same time these 3 clips that were also laser beam welded were actually unnecessary and even detrimental for the structural integrity and life of these panels. So you can see here some results both from testing and from extended finite element method simulation. So it's time to make conclusions. We can say first that in order to make future bright, one has to know the history. And this is because inspiration for new achievements is often hidden and not so obvious, to say at least. So we really need to know history in more details. And these historical aspects that we cover here using structural integrity examples indicate that all of these extraordinary achievements are driven by need to show the power or in some cases by economy. But in both cases, human ingenuity was needed to perform the task. That was not a simple process. We can really end this presentation by stating good old Latin say, per aspera ad astra. Thank you for your attention.